laboratory number 2. The purpose of this lab is to measure the distance dependence of a magnetic dipole and a bar magnet. Then I'm going to create a computational model to predict the magnetic fields based on the distance dependence. Then I'm going to compare the model to the actual measured magnetic field. A preview is that the magnetic field calculated by the model is 4.02 times 10 to the negative 6 Tesla, and the magnetic field that I measured is 3.725 times 10 to the negative 5 Tesla. Some fundamental principles. First, we have the Biot-Savart law, which is the equation that you see right here for magnetic fields. We also have the magnetic dipole, and so basically this is when the observation point is very far from the magnet, then the magnet acts as a dipole. When the observation point is parallel to the magnet, then we use this equation, and when it's perpendicular, we use this equation. And then finally, we have the distance dependence formulas right here that we're going to be using in the first part of the lab. For the experiment, we have the system, which is the bar magnet, and the surroundings, which is everything else. The initial conditions, we have a small bar magnet is placed close to an iPhone with a Tesla meter installed, and this is an app that basically measures the magnetic field. And so first we have to make sure that the iPhone is aligned with the Earth's north-south axis, and when this is done well, the x component will be about 0. Then I aligned a meter stick perpendicular to the iPhone, which will be on the east-west axis. Then I gathered data for the distance dependence by measuring the magnetic field at different distances on the east-west axis. And then finally, I measured the magnetic field at a distance off the axis at about a 45-degree angle, as you can see in this picture here. Some observations. So when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and this is basically because we can approximate the magnet as a dipole, and so it really only has one direction, which is like parallel to the magnetic dipole moment. And then also we can see that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases, and this is because we can no longer treat the magnet as a dipole, and it's going to have an x and y component. So some results from my experiment. I used the Excel spreadsheet to enter in a lot of my data, and I got the equation for distance dependence here. And so we can compare this equation to the equation that we had earlier in the fundamental principles. And so we can see that ln of k is equal to this value right here. And then just solving for k, we get 4.94 times 10 to the negative 8. And then n is just the slope of this equation, and then r is the distance, which is 1. And then in order to find the magnetic dipole moment, we just have to make these two equations, we set them equal to each other, and then solve for mu, and then we're going to get 0.494. So for our computational model, I just have to insert that value, 0.94, into my model. And this model assumes that the magnet is acting as a dipole so that it is very far from the observation. So here's my model continued, and then as we can see here are the magnetic dipoles, and then this is the magnetic field at 45 degrees. Yeah. So comparing some results, from the model we have the magnetic field to be this value, and then the magnitude is 4.0261 times 10 to the negative 6, but the actual measured magnetic field that I got from my iPhone was 3.725 times 10 to the negative 5. They're somewhat similar, but still pretty different. So this could be due to some source of error, like my iPhone sensor could have been a little inaccurate, and also it's difficult to locate the sensor in my iPhone to get the correct distances. And also my assumption that the magnet was acting as a dipole could have been incorrect. So finally, we have some discussion questions. What if I didn't properly orient my iPhone? How would my results have changed? Basically, this would have made my results pretty inaccurate because the x component of Earth's magnetic field would not have been 0 anymore. And so I would have attributed all of the x component to the magnet when it was actually also because of the Earth. So then this would have messed up my magnetic field readings. And then what if I had two magnets? How would this change? So basically the magnitude of the magnetic field would double since there's two magnets, but the magnetic dipole moment would stay the same because they would both have the north and south in the same direction. Thank you.